Welcome to day 3 of Introduction to Fluid Flow. Today we are going to talk about Newton's second law in fluid dynamics and how it connects with the momentum equation. Let's start with the basics. Newton's second law. It is F equal to ma. This can also be written as F equal to d by dt of mv. Here d by dt of v is just acceleration because acceleration is time derivative of velocity. This can also be read as force equal to rate of change of momentum. We apply this to a control volume and then we can say that net force equal to rate of change of momentum inside volume plus momentum flow across control surface. Just hold on to this concept because in a minute it will help us clearly understand the momentum equation derivation. The physical principle behind momentum equation is force equal to time rate of change of momentum. We apply this principle to the finite control volume. Let me quickly explain this diagram. This represents the control volume. Here, dV is a tiny fluid element inside the volume. ds is a small surface area element on the control surface. V is the total volume inside the control volume and S is the boundary of that volume, that is the control surface. The V here is the fluid velocity vector showing direction and speed of the flow, and ds pointing outwards is a normal vector to the surface ds. This setup helps us apply the momentum equation properly by analyzing what's happening inside and across the boundary. Now let's look at the left side of the equation, force. It is the force exerted on the fluid as it flows through the control volume. It comes from two sources. One is body forces like gravity, which acts at a distance on the fluid inside V, and the second is surface force, which is pressure and shear stress acting on the control surface S. Let force F represent the net body force per unit mass exerted on the fluid inside the control volume V. In this case, the body force on an elemental volume dV is represented as rho F dV, where rho dV is the mass of the fluid inside that small volume dV. And F is the force per unit mass, which is essentially the acceleration. So, just like the equation force equal to mass into acceleration, we can say that force in the volume is rho dV into F, where F is acceleration. Next, the total body force exerted on the fluid inside the control volume V will be the volume integral of rho F dV. Now let's move on to the surface forces. The elemental surface force due to pressure acting on an elemental area ds is minus pds. The negative sign indicates that the force is acting in the opposite direction of surface normal vector ds. Finally, over the complete control surface, pressure force equal to minus surface integral pds. In a viscous flow, the shear and normal viscous stresses also exert a surface force. We denote that as F viscous. Now that we have discussed the left side of the equation, which is the total force, it includes both the body force and surface forces, which is pressure and viscous. So, this is our complete expression for force, that is F equal to volume integral of rho F dV minus surface integral of P ds plus F viscous. Now let's move on to the right side of the equation, the time rate of change of momentum. This side has two parts. The net flow of momentum out of control volume across surfaces denoted by G, and the time rate of change of momentum due to unsteady fluctuations of flow properties inside V denoted by H. Let's talk about G first. This represents the flow of momentum across an element area ds on the control surface. For an incompressible fluid, this is given by rho v dot ds into v. where rho v ds is the mass and v is the velocity. So mass into velocity is the momentum, the thing which we are talking about. And over the complete control surface, it is surface integral rho v dot ds into v. Now let's move on to the term h. The momentum of the fluid in the elemental volume dV is given by rho dV into v, where rho dV is the mass and v is the velocity, and mass into velocity gives momentum of the fluid. And over the complete control volume, it is given as volume integral rho v dV. The time rate of change of momentum due to unsteady flow fluctuation is h equal to dou by dou t of volume integral v rho v dv. Combining all the equations, that is F equal to ma, that is equal to d by dt of mv is equal to g plus h is equal to surface integral of rho v dot ds into v plus dou by dou t of volume integral of rho v dv. By combining the left and right side of the equation, that is f and g and h, we get the following equation. This is the momentum equation in integral form. To convert this into partial differential equation, we need to apply gradient theorem to the first term on the right side of the equation, that is minus surface integral pds equal to minus volume integral del dot pdv. Also, because the control volume is fixed, the time derivative can be placed inside the integral. So that gives us this equation. Now we have the vector equation. To convert it into a scalar equation using Cartesian coordinates, we express the velocity as a vector, that is v equal to ui plus vj plus wk, where u, v, w are the velocity components in the x, y and z directions respectively. The x component of the equation will become like this. This is a straightforward process where we add the u component to every term of the equation. Take a look here. This is very similar to the earlier equation that we solved. You can write it out for better clarity. Next that we apply the divergence theorem to convert the surface integral to volume integral, and finally putting it into the equation, we get the following final equation. Since this equation must be true at every small part of the flow, the only way that can happen is if everything inside the integral is 0. So we just write that part directly as an equation. This gives us the x direction momentum equation, that is dou rho u by dou t plus del dot rho u v equal to minus dou p by dou x plus rho fx plus fx viscous. This tells us how the flow speed in the x direction changes because of pressure and external forces like gravity. These equations can be used for any kind of flow, whether it's steady or unsteady, 3D or not, compressible or incompressible, and whether the fluid has viscosity or not. But in special cases, the equation becomes much simpler. If the flow is steady, then the dou by dou t term becomes 0. If the flow is inviscid, then the viscous force becomes 0. If there are no body forces like gravity, then F equal to 0 too. So with all these conditions, the momentum equation becomes surface integral rho v dot ds into v equal to minus surface integral pds in integral form, and del dot rho uv equal to minus dou p by dou x in differential form. If you found this helpful and want clear, easy to understand notes, drop a comment below. And if you learned something today, don't forget to support the channel. Your support motivates me to share more simple and precise concepts in aerodynamics that everyone can follow. Thank you for watching.